Hello everyone, I'm excited to present our work titled Hybrid Concept Bottleneck Models, which tackles a fundamental challenge in machine learning: how to build interpretable models, especially for vision tasks. Deep neural networks have achieved impressive performance, but they often operate as black boxes. In critical domains like healthcare, finance, and education, interpretability is just as important as accuracy. We need to understand why a model makes a decision, not just what it predicts. Concept bottleneck models were introduced to address this challenge. They follow a two-stage process. 1. Predict a set of human-understandable concepts from an image. 2. Make a final prediction based on those concepts. While CBMs enhance interpretability, they face two significant limitations. 1. They often underperform compared to black box models. 2. They require precise and manual concept annotations for every image, which is costly and not scalable. As shown in the image, CBM need require human to predefine concepts like feet on the ground for each image. To address this, we introduce learnable concept vectors that can discover missing or overlooked concepts, such as yellowish throat, automatically during training. This improves flexibility and reduces manual labor. To overcome these challenges, we propose hybrid CBM, which integrates a static concept bank, using predefined concepts generated by language models like GPT-3.5. A dynamic concept bank, consisting of trainable vectors that learn new concepts during training. A pre-trained concept translator, based on GPT-2 to convert dynamic vectors into human-readable descriptions. The training pipeline uses CLIP to align image and text in a shared embedding space. Static concepts are derived from language models, while dynamic concepts are learned directly from data. After training, our translator turns these abstract vectors into understandable phrases. The result: improved interpretability without compromising performance. But how do we ensure that the learned dynamic concepts are meaningful? We design a concept interpretability training scheme, which regularizes dynamic vectors using three losses. Discriminability loss encourages concepts to activate for specific classes while remaining inactive for others. Orthogonality loss ensures that concepts within the same class are diverse and non-redundant. Distribution alignment loss aligns the distribution of dynamic concepts with that of static ones. Together, these guide the model to learn concepts that are discriminative, diverse, and semantically aligned. We compare hybrid CBM against traditional black box models using CLIP-VTL/14 in both fully supervised and few-shot settings. As shown in Table 1, hybrid CBM performs competitively in the full setting and significantly outperforms in the few-shot case. Further comparisons, summarized in Table 2 using CLIP-RN50 for fairness, show that hybrid CBM achieve state-of-the-art performance across multiple datasets and CBM variants. We conduct a deeper analysis using the CUB dataset. The concept class correlation map shows strong alignment between dynamic concepts and their respective classes. The concept-concept correlation map reveals meaningful semantic structure. Classifier weight visualizations indicate that dynamic concepts are more discriminative than static ones. We also compare submodularly selected concepts versus random selections in Figure B. The former are clearly more coherent and class-relevant. To evaluate the interpretability of the dynamic concepts, we design metrics for two aspects: feature level and concept level. For feature level, concept purity, how well each concept aligns with a specific class. Separation, how distinct the concepts are across different classes. For concept level, we prompt GPT-3.5 to verify if each translated concept accurately describes its class. We use GPT-4o for concept retrieval, measuring precision at Ka, the proportion of top concepts GPT-4o confirms as relevant for a sampled image. Specifically, we prompt GPT-3.5 to evaluate each translated concept's accuracy in representing a specific class with a binary yes or no response. We calculate the proportion of concepts that GPT-3.5 correctly associates with the intended classes. For concept retrieval, we use the ability of GPT-4o in image understanding to calculate The retrieval precision at K. For a sample image of each class, we measure the average proportion of K concepts that GPT-4o confirms as relevant. We evaluate hybrid CBM static and dynamic concepts using the metrics defined above. For static concepts, submodular selection outperforms random selection in semantic score, 38.3% versus 30.9%. For dynamic concepts, incorporating the tree loss functions boosts their semantic score to 32.8%, approaching that of static concepts. This demonstrates the effectiveness of our losses in enhancing the alignment and discriminative power of dynamic concepts. Interpretability can be viewed in two forms. Pattern level, understanding general patterns the model has learned. Case level, explaining decisions on a per-instance basis. As shown in the figure, we illustrate case-level interpretability by selecting the top two concepts for each image and evaluating their accuracy using retrieval precision at K. This offers a transparent explanation of the model's prediction for individual examples. In summary, hybrid CBM bridges the gap between performance and interpretability by combining predefined and learned concepts, reducing reliance on manual annotations, enabling transparent predictions with strong performance. Thank you.